Still have the three very important property we didn't teach before. The first one is the surface tension. The second is the vapor pressures. The final one is the specific heat. Okay, we still have the, as I mentioned in this chapter first, totally we have the 7 fluid property we need to know from these chapters. So until now we have teach the 4 property before, and we still have the final 3. So the surface tension, what is the surface tension? So you see the sentence I write down in here, the physical mechanism of the surface tension is based on the cohesion force. So what is the cohesion force? If the two, we have like the water, and we surrounding material are the water molecules. So they are the same material. The same material we have the coefficient force. Okay? So that means if the different material, the boundary between the different material, there are some external force. Okay? Okay, so that's the what is the cohesion force? The cohesion force is an attractive force between two same molecules. Okay, so if the different molecule, we can we will have the different coefficients. Okay, so as the example showing here, this is the water. Here is the water, and you see the circle is the water molecules, and above the water surface there is the air, right? So the boundary in here, so we have a certain boundary in here, and the molecule along this boundary would like to downward because there are some interaction force between two different water molecules. So in resulting, you will see the surface of the water in here will change the shape, maybe like this shape, not always flat. Because the upper is air and the down is the water, then same material will have the coefficient force. So the shape on the water surface will change, not always fix the flat. Okay? So, but what are the purposes? So I just highlight the sentence. The surface tension would like to seek to minimize the surface area. Where is the surface area? If there are two different materials, so the surface area is along the interface in here, and this interface area will minimize the interface area due to the surface tensions. That's why you can see always the water will become the bubble. Why the water will become the bubble? Because the spherical shape is always the smallest surface area. If your shape is not a spherical shape, the area should be larger than spherical area. So that's why you put the water, and sometimes you can see the water become a bubble, because this is due to the surface tensions, and the purpose we like to minimize the surface area. Okay, so I just highlight some important physical phenomena there are corresponding to the surface tensions. If you can see here, like the weakens and the capillary rise and the bubble formations and the pressures, because we would like to form the bubbles, we have the inside pressure in the bubble and the outside ambient pressures, and we can calculate the inside pressures, how large inside pressure we have for the different diameter of the bubbles. So the two phenomena, they are the same physical meanings. And you can see some insects can walking on the waters. Okay, like the 轻功水上漂，对不对？ So walking on the waters, like I show the one example, strider, the strider 水蜘蛛. Okay, so that's why they can just moving on the water, that because it's due to the surface tension phenomena. And also the detergents, how can we use the detergent to wash the dirty material away? Because the detergent will broken the surface tension, the coefficient between the water molecules. So the water molecule can freely to move and slide and wash anywhere have the dirty material. If you don't broken the water surface tension and the coefficient force, the water will always flow on the same ways. So that the detergent can broken the coefficient force between the water molecules. So the water molecule can free anywhere to wash homogeneous dirty material outside. Okay, so in the following slides, we will have some exercise and we will introduce more details. So right now we go back to see the unit of the surface tensions. Usually we use the sigma to be the surface tension. Okay, and then the unit here, you see the force along an interface per unit interface length. And what is the force? The force is the coefficient force along an interface. Why should be along the interface? Because we focus on the phenomena only can happen along the interface between two materials. So we just focus on the material difference boundaries. So that's why the force along the interface per unit interface. Okay, so the unit here you can see is newtons per meters. Newton per meter. If we multiply additional meters both sides, so upper we multiply the meter and the down also the meters. So as you can see, the dimensional will change to the joule and the meters square. So additional physical meaning for the surface tensions, it indicates the energy required when you would like to increase the surface areas. Because the original purpose, we need to minimize the surface area. But if you would like to increase your unit area, so how many energy you need? Okay, so that's why that here we have a different unit but the same physical meanings. Okay, so the right hand side figure showing here, this is the watt for the water. And you see the function along the x is the temperatures and the y is the surface tensions. And so you see the blue line is decrease. That means the negative slope indicates the surface tension will decrease when the temperature increase. So as I mentioned, the surface tension like the coefficient between the same molecules. So the temperature increase, you will provide the energy to broken the coefficient force. Okay, you provide the energy to break the interaction between two molecules. So that's why the surface tension will decrease when the temperature increase. Okay, so that's a very important common sense. At the room conditions, the surface tension for the water is equal to 0.0728. Okay, so you can maybe for this number you can keep in mind. It's like the common sense in fluid mechanisms. Okay, so we move to the next. So in the previous slide we focused on explain how about the surface tensions, and we always tell you that's the important thing is the cohesions of the two same molecules, right? But if we put on the different material, like here, this is the glass. And if you put the water on the gas, and then you see the shape. So here you can see the shape of the water is the flat. Do not become the bubble. So that means along this boundary, the force along this the blue line boundary, we call that the adhesions. Different material, we will have the different force. But the same material, we only have the cohesion force. Okay? So that means the adhesions larger than cohesions. So the water cannot become the bubble. Because the adhesions, like it fix in the boundary, cannot form the bubbles. So this is for the glass material. If the water put on the glass, so you can do the experiment by yourself. You just put the water in the glass. Okay, you can see the water cannot to form the bubbles, but you can put the water into the Teflon, and you can actually see the bubble waters. Okay. That's because the water cohesion force is larger than the adhesion between two different materials. Okay, so you can consider some different phenomena. And for the above case, we call that is the water loving. Okay, and the bottom is water hating. And there's some words. We can say that it's a hydrophilic or hydrophobic, but it is too similar, difficult to remember, right? So usually I just remember the water hating or the water loving. Okay, so you can, but the key knowledge in here is adhesion and cohesion. You just compare which one is larger. And if the adhesion is larger, that means the material is water loving. If the cohesion larger than adhesion, and we call that is water hating. Okay, so you can just keep in mind for these properties. Okay, so this the first exercise we focus on the capillary actions. Okay. As you see the figure showing here, the key knowledge is from these images. We first one know that the diameter of the tube is different, right? So this is the diameter here, D, and then the final one, the D, the diameter from left to right is decreased. This is the first one. And how information we can capture from the images is the rise height. As you can see, the rise height, we use the delta H is total difference. Okay, and in here is a higher one. So that means the different diameter of the tube will control the different rising height of the liquid. Okay, so we would like to prove this phenomena. So we would like to derive the formula to better understand the relationship between the diameter of the tube and the rise height. Okay, so this is our D, and we have the delta H. So the first one, like the bottom figure showing here, we actually know the rising height is delta H, and we have maybe this is the water. So the liquid is the water, and we actually know this is the water columns. So first one, we assume the water is cylinders, like the shape like this, the rising columns. So we have the rising water columns. So this is our water, like the figure showing here. Okay, so and for this, we have the weight, right? We have the weight downward. This is a weight caused by the waters. And we should have the surface tensions. We have the surface tensions acting along the circle radius. So we have the surface tensions acting on the circles. So this is our surface tension force. So we have a surface tension force upward, and we try to overcome the downward weight. And we still make the force balance. Okay, so we first focus on the weight of the water. If we know the water gamma is specific weight, right? And if we know the volumes of the water, so we can compute the gamma, compute the water weight. Okay, so in here, we actually know the gamma W, right? So how about the volumes of the waters? So we consider this is a cylinder shape. So we compute the area of the circle. So we actually know the diameter is D. So half diameter squared pi is the circle area, and multiply the delta H. So these items is the volumes of the waters columns. Okay, so we can just reorganize the equation here. So this is the 4 over D squared pi gamma W delta H. Okay, this is the weight. And how about the surface tension force in this problem? So we have the surface tension, sigma. And we call that the surface tension always happens in the interface boundary. So here the interface boundary is the circle length. So the circle length, we actually know the circle length is equal to the diameter pi, right? It's a circle radius length. Okay, so the sigma multiply the d pi. Okay, and then this is the surface tension force. Okay, so if you don't know how to compute the surface tension force, but we have the certain definition. The unit of the surface tension is the Newton per meter. So you need to multiply the length of the interface, and then the unit for the F sigma is the Newton. Okay, so the dimensional is consistent. Okay, so but one idea I didn't mention is the surface tension force working here. You see the F sigma, they are not always upward, right? This is oblique force. And if you would like to project to the upward, you need to do the additional cosine theta, right? You need to project the F sigma into the vertical directions. Okay, so we can make the force balance is the F sigma equal to weight. Okay, so we have the sigma d pi cosine theta is equal to 4 over d squared pi gamma w delta h. So you look at some same parameter d, and we cancel out the 1 times of the d. And the pi, they are the same, both sides. So we rearrange the equations, we put the delta h on one side, and we move to other parameter is 4 sigma cosine theta divided the gamma w d. Okay, and because the theta angle is quite smaller, so that indicates the cosine theta will equal to 1. Okay, it's about equal to 1. So finally, you can see the final formula showing here. There is no cosine thetas. There is no cosine thetas. Okay, and the gamma here, just use the gamma. Don't use the gamma W because you can change the different liquid. And you can see how different liquid property will have a different rising height, even though you fix the diameter of the tube. So the key knowledge for these problems, you can focus on here. The formula just directly tell you the reason why the small diameters will have the higher rising heights. Okay, and also depend on how liquid you use and how the interface. The different interface, you will have the different material, you will have the different surface tensions, and you will have a different specific weight. Okay, but here our key knowledge is we keep the same liquid, but we try to observe how change of the rising height depend on different tube diameters. Okay, so you can do the exercise as the movie showing here. Initially, I just put a different tube and I push in the water inside, and then you can see the different rising heights. And the right hand side, the final one, we need the time to balance the force, right? So the water just moving up slowly until the force balance. Okay, so this is very important for the surface tension phenomena. So, but some different idea you see why the liquid will rise. That's because the boundary is, you consider the condition is between the water, between the water and the gas. If you change the water to mercury, and the phenomena total change, you see the mercury cannot rise, it's just a downward. That's because, as I mentioned, you need to compare the different properties. The first one is adhesion, and the second one is cohesion. Which one is large? If the adhesion is large or cohesion is large, you will see the different phenomena. Okay, so you need to if you look at the problem and then you see, you need to double check how material you use, and you can observe the different phenomena. So for the mercury, we need to consider how the downward weight, downward high. But for the water, we see how the rising high. So the physical phenomena is the difference. Okay, so and this is the for the bubble questions, why we can see the water become the bubbles, And some idea is we need to require the pressure inside. That means the pressure inside the bubble if higher than in ambient pressures, and then the bubble can be the spherical shape, right? If the pressure inside the bubble are not larger than in ambient pressure, the bubble will break. So we need to overcome the environment pressures. So we need to have the inside pressure first, and then we can form the bubble shape. Okay, so that's the exercise. We'd like to teach you how to calculate the inside pressures. If you already know your bubble size is 2 millimeter diameters, and how can you decide the pressure inside the bubbles? Okay, so because I forgot to record in the previous, so 我用中文稍微再讲一下，把它录下来。第一个是我们用库尔特 flow 最后一个 exercise 来理解一下正常我们在库尔特 flow 会遇到的状况，主要都是去调整材料的厚度，或者是你替换掉材料就有不同的粘滞性质，那你就可以去控制上方的这个 sliding 的 speed。那我们最后有3个physical property 要继续解释的，一个就是表面张力 surface tension， 那下一个就是我们说的这个除了表面张力以外，我们还有一个比热，然后还有一个蒸汽压力 vapor pressure。OK， 那表面张力其实它就是一种作用力，想要让只要你物质之间有什么2个物质之间不一样，就会有边界嘛。那它会想要让这个接触的边界的表面积是最小的，那就是表面张力的物理性质。所以它当然同一种性质的材料，它就只会有内聚力。那不同性质之间的这个边界就会有什么？这个就是我们刚刚说的这个 adhesion 就附着力。所以你会一直在强调不同材料的附着力跟内聚力之间，它们怎么样去调试，那才会有什么亲水跟厌水性的这些材料让你去看。那最后就会有这个，因为有这种表面张力的作用，你就会有的性质是抬升，有的性质是下降，这样子。不是说每一个液体你放到玻璃管里面它都会抬升，那就是你要去 overcome 那个你跟玻璃管之间的内聚力的这个附着力。那如果你沒辦法 overcome， 你反而被附着力控制住的話，那你就會有不同的表現這樣子。Okay, so a little bit complex, so maybe we just start here and we have a 10 minutes break. And we still have some exercise. We just finished, and today we will finish the chapter 2. So the next week, the test, the quiz only focus on the final chapter 2 contest. OK， 好，那我们休息10分钟。